Hi guys, this is Vishaal and Shreya, and we are here to talk about our project that's titled Product Recommendations Using Heterogeneous Data. A quick overview of the topics that we'll be discussing today. We'll first go over the research statement for our project, and we'll describe the motivation for our project. We also talk about a couple of papers that have been published that's related to our work, and we'll describe the data set that we use for our experiments, and then we'll also talk about the methodology and the experiments that we performed, and finally the results that we got. So our research statement is to use heterogeneous data to make better product recommendations. So examples of this data could be images, reviews, and product metadata like price of the product and other features that the product might have. So our motivation comes from how users tend to browse products on online retail websites like Amazon. So you have an example here of a shoe, and things that you might look at would be the image of the product and what the product title is, the brand, and which version of the product this is, and the price, and other features that the product might have like rubber sole and textile and synthetic in this case. And we also look at things like the reviews that other users might have written, because these reviews actually contain information about the product itself and feedback from other users. So examples of this would be that this shoe is not as cushioned as the ones in the past. These shoes are very expensive and so on. So we want to make use of all these different kinds of data that is present in a product on a website, and make better product recommendations. Features that are used to make product recommendations can be broadly classified into metadata, reviews, or images. So what you see on this slide is examples of papers that makes use of different combinations of these features. The class of work that uses images to make product recommendations is fairly new and fairly recent, and our goal actually stems from the fact that there's hardly been any work that tries to make use of all these features and tries to make better product recommendations when we have enough reason to believe that that could actually work better. So I'll quickly describe the data set that we use in our experiments. So we use product data set that was collected from Amazon over a period of 18 years. So this includes 24 product categories. The reviews also include ratings that the users gave the product and the helpfulness that other users found from the review. The dataset also includes metadata about the product, which includes image features and description, category information, and so on. So the data set is actually really rich and is really large, and we also have information about we also have co-purchasing information and things like users who viewed this product also viewed this product, the users who bought this product also bought this product, and so on. So the first experiment that we performed was rating prediction. So here we assume that the rating that a user gives is an indication of the overall satisfaction that he has with the product. So what we try to do is to model this rating as a combination of a bunch of features, the features that we described before, the image features, review features, user embedding, and product embedding. So I want to talk about these embedding vectors. So there is a matrix of size, number of users times the dimension of the embedding. And similarly for the product, we have a matrix of size, number of products times the embedding. And given a user and a product, we basically fetch one row from the matrix for the user and one row for the product, and this would be the feature that is fed into the feed forward neural network. So we start with a random initialization for these two matrices. The image features are actually VGGNet features that were downloaded from the internet. For the review features, we use average word vectors after removing stop words, and we basically feed all these features into a neural network and try to predict the rating. Um, uh, we also want to point out that these user and product embeddings are also trained using back propagation. So finally, during testing, when you give a user UI and a product VI, we'll basically pass that through the same neural network to find what rating he would have given the product. One more reason why we chose to do this experiment was that we can find out which feature adds most value to making recommendations. So what I could do is I could mix and match between these features and find out which gives me the best performance, and also figure out whether, say, image embeddings lead to better performance and so on. So we also wanted to find out whether all these features put together would actually make product recommendations better. That we use for evaluation is the mean square error between the predicted and the actual rating. The left-hand side column includes information about the combinations of features that we tested. U stands for user embedding, V stands for product embedding, R stands for rating vector, and I stands for the image vector. So the performance wasn't actually as great as we expected it to be. Remember that what we plot here is the mean square error, so lower is better. We expected using all these features together to give us the best performance, when in fact using reviews gave us a huge boost in the performance, whereas using the image features didn't lead to that much of a difference. So we have a bunch of reasons why what this could be due to. So the first reason is that we don't really make use of any other information about the product, and we also don't make use of the purchasing information that is present in the dataset. The model also doesn't pay attention to subtle image similarities. We have a very naive way of concatenating features and feeding them to the network. So we don't really make use of the correlation between review and the feature vectors. So that could be reasons for why this model didn't perform as we expect.
Now I'm going to be describing our methodology. Our pipeline is a Siamese network that optimizes the contrastive loss function across a pair of product embeddings. Now, each of these terms I'm going to be describing in more detail in subsequent lectures, as well as our design choices would be explained later. But for now, we have a broad overview. We start out with a pair of products, and for each product, we combine its pre processed image, review, and metadata features to get one vector per product. The exact pre processing steps are described in later slides. We feed these vectors into different branches of a Siamese network. Each branch passes a vector of size 600 through two dense layers, and both of those layers have associated activation layers as well as a dropout layer. Now, for activation, we use a tan h function, and our dropout fraction is 0.5. Both these layers produce a 256 length output vector. Both branches of the Siamese network have tied weights, which ensures that the transformation on both product vectors is identical. The output of these layers is then fed into a distance layer that uses the Euclidean distance between the two vectors and optimizes the contrastive loss function to ensure that similar products are embedded close together. I'll be describing the contrastive loss function in more detail in later slides. Finally, the embeddings that we obtain for both products are the outputs of the Siamese network. So for figuring out the embeddings, we remove the distance layer and consider the output as a final embedding. I'm now going to be describing my pre-processing steps in more detail. And I'm also going to be describing how we tailor our pre-processing to the type of data that we have for our heterogeneous data sources. So starting out with images, we use feature vectors extracted using a VGG and the size of the feature vectors that we start out with is 4096. We then perform dimensionality reduction on this feature vector using PCA to find a final dimensionality of 300. We had experimented with the sparse autoencoder as well, but we found that PCA works better in practice for us. Moving on to reviews, we start out by aggregating the reviews per product. The assumption that allows us to do that is that reviews by different users on a single product are independent of the user preference themselves, since users tend to discuss the product more in the review than their own personal choices. This is an assumption that holds in other papers that are published in this area as well, so it's a common assumption. We then experimented with two methods. The first method that we used was using topic discovery. More specifically, we used the latent dirichlet allocation algorithm, and we discovered review dimensions using topic modeling. We finally scored the features per document using the probability of the topic given the document. This allows us to get a feature vector of size number of topics for every document. Our second method uses document embeddings using Word2Vec. So Word2Vec is a very popular paper that has been used in multiple sources that provides an embedding per word, and aggregating that across documents consists of taking the average of every word in that document after some pre-processing, such as removing stop words. Moving on to metadata, the most critical feature that we obtain from our metadata is the product graph. This has many different relationships between products, such as products that were viewed together, products that were bought together, products that are similar in category, etc. So we have 4 different relationships between the products that we finally use to learn our embeddings as well. We also use the price feature directly for our training net. So since price is a very important dimension of a product, and allows us to figure out if two different products are similar to each other, so without any pre-processing except for normalization, price is used in our training nets. We also have category-wise information that is present in our dataset. However, for our task, it is not relevant, since we're only restricting our experiments to the clothing section, to the clothing category of the Amazon dataset. We now have a visualization of each branch of the Siamese network. Since the weights are tied and the branches are identical, both of the branches look exactly like this. So the first layer in the Siamese network is the input layer. The number of units in this layer are 600, corresponding with the dimension of the product feature vector. This layer passes the input into a dense layer of comprising of 256 units. The dense layer has associated with it an activation layer as well as a dropout layer. After passing through the first dense layer, the vector passes on to another dense layer with identical activation and dropout layers associated with it. The activation function that we're using is tan h, and the dropout layer parameter is 0.5. Moving on, I now describe the contrastive loss function that we're using in more detail. This function is taken from Jan LeCun's seminal paper on dimensionality reduction. The intuition behind this loss function is the following. Consider this blue circle that represents a product, and let the second blue circle represent another product that is similar to the first one. So for an embedding to be high quality, the distance between these two products should be close together in the embedding space that is finally learned. Similarly, for another product that shares a relationship with these two products, the distance should also be close to them in the embedding space. Therefore, if there are two products that are similar to each other and are put through the Siamese network, the network should minimize the distance between the embeddings learned between these products. However, if a product is different compared to these other blue products, then its distance from these products should be maximized in the output of the Siamese network. Let's look at another different product. This product is already far away from the blue products in the embedding space. Imagine, so To put things into perspective, imagine a circle of margin M that surrounds the blue products. So this new orange product lies outside the circle of influence. Therefore, we don't further try to increase the distance between this product and any other blue product because it's already outside this circle. Now, let's mathematically formulate the intuition that we came up with. Here is the mathematical loss function that we're minimizing. I'm going to be describing the symbols that we use in this function. So x1 is the product embedding that is at the output of one branch of the Siamese network, and x2 is the product embedding that is at the other branch of the Siamese network. Let y be a binary variable that denotes if the products are similar or different. So this variable is 0 if the products are similar and 1 if they're different. L represents a loss function between any two products x1 and x2 and the relationship between them y. And d of x1 and x2 is the distance between the embeddings of product x1 and product x2. The distance function that we are using is the Euclidean distance. Now, this function basically implements this intuition in the following manner, that if two products are similar, then their y variable will be equal to 0, in which case the loss function is going to be equal to the distance between them. Since we're minimizing the loss function, to maximize our performance, we would end up minimizing the distance between these two similar products. In contrast, if there is another product, if there's a pair of products that are dissimilar, then the y variable will be equal to 1, in which case the loss function will be equal to the maximum of 0 and m minus d x1 x2. Here m is the radius of the circle of influence. So we can see that if the distance is less than or equal to the margin of the circle of influence, then the loss function will try to maximize this distance in order to minimize the loss. And if this distance is greater than the circle of influence, in that case the loss function, the neural net, will do nothing. So we see that we encapsulated the intuition that we have for our different loss function into this mathematical formulation. I am now going to be describing our evaluation strategy. So the metric we plan to be comparing on is accuracy at top K. This is a very commonly used metric for product recommendation, and it basically means that if in top K similar predictions, there should be, if there is at least one true positive inside the prediction, then the prediction is considered successful. The idea is that even if the consumer buys one product that was recommended, then the recommendation process is successful. The baselines that we plan to be comparing against are the following. The first one is our own constructed baseline, which basically uses embeddings generated exclusively from image reviews or meta features only, without combining all three of them together. The second baseline that we plan to be comparing against is a recent item to vec paper that learns embeddings based on co-occurrence without any product content based information. And the third is a standard SVD style embedding methodology. Finally, we describe our semester progress that we have completed and that we're in the process of completing. So our solution formulation, our dataset collection, hypothesis testing, as well as implementation is finished, and we are currently in the process of writing code for our evaluation strategy. So with that, we finish the presentation and we leave you with our references. Thank you.